Hello guys, my name is Lazaro and today we're going to be doing a LeetCode problem. This problem is called Flatten a Multi-Level Doubly Linked List. You're given a doubly linked list which contains nodes that have a next pointer, a previous pointer, and an additional child pointer. This child pointer may or may not point to a separate doubly linked list also containing those special nodes. These child lists may have one or more children of their own and so on to produce a multi-level data structure as shown in the example below. So here we go. This is what I mean by multi-level. This node 3 has a child that points to 7. And then inside this list, starting at 7, node 8 also has a child that is just 11 and 12. So you can think of this as 3 separate lists. And that's what I mean by multi-level. So given the head of the first level of the list, flatten the list so that all the nodes appear on a single level doubly linked list. Alright, so we know what we want to return. We just want to return one list that is all in one level. Let cur be a node with a child list. Okay, so cur, for example, can be 3 because it does have a child list. The nodes in the child list should appear after cur. Alright, so 7, 8, 9, and 10 should appear after 3 and before cur.next in the flattened list. Alright, and then 10 should appear right before 4. Return the head of the flattened list. The nodes in the list must have all their child pointers set to null. So this is the first example. I'm actually going to write it out, or write out an example similar to it in the notebook. This might be pretty big, so let's see if I can make it exactly as this first example. Okay, so here's the list. We have the multi-level data structure where 3 has a child that points to 7 and 8 also has a child. So what do they want us to do? Well, first we need to recognize other nodes that do have children. In this case, it's just 3 and 8. And what we want to do is take the children list and put it right between the node that has a child and the node that has a child dot next. So if we were to transform this on the first go, we would have 1, 1 points to 2, 2 points to 3, 3 points to 7, 7 points to 8. And we want to take this list and put it right in between 8 and 9. So 8 is going to point to 11, then 11 is going to point to 12, then 12 to 9, and then 9 to 10. Then going back here, same as before, 4, 5, and then 6. Now we notice how 3 still has a child list. So we want to do pretty much the exact same thing. Take this whole list right here and put it right in between 3 and 4. AKA as I had in the problem where this is cur and this is cur.next. They said to put the list between cur and cur.next. Now I don't really have space on canvas and I feel like it'll be kind of repetitive, but you understand that how it would look. It would be 1, 2, 3, 7, 8, 11, 12, 9, 10, 4, 5, and 6 all in one list. And then we would change this pointer to point to null. So how do we want to do this? Well, the first thing that we want to realize, should probably erase, can't go back anymore, is that once we reach a node that has a child, we want to separately keep hold of its next nodes. So once we get to 3, we realize 3 has children. So let's keep a hold of this 4, 5, and 6 somewhere. Let's just place it on the side. In fact, I am going to do that. See if I can make this work. Perfect. So let's keep this 4, 5, and 6 on hold for now. And let's change the child node, the child pointer of 3. Let's make it look to something as none. So let's change this, make it look to none. And let's make the next of 3 be its children. So this is just so far some really small rearrangement. So what we're going to be doing is pretty much bringing it right there. And we're going to be setting this child pointer to null or none. And then let's continue iterating through this. So now we have 7, then we have 8. And now 8 also has a child. So first let me just erase this. Now 8 also has children, or a child pointer that's not none, and it contains 11 and 12. So just how we did for 3, let's hold the next nodes of 8. Whoops. Let's hold the next child nodes, the next nodes of 8. Put it right here, for example. Let's move its children list to be its next nodes. And let's also set the child pointer to none. So far this is looking pretty good. We have 1, 2, 3, 7, 8, 11, 12. But once we get to 12, what do we do? Well, this 12 is pointing to none, so should we stop here? Well, we really shouldn't stop. The reason we don't want to stop is because we have nodes that we were holding on to, and we eventually have to bring them back. Just gonna give myself some more room here. And we eventually have to bring them back. So while the next pointer does not point at anything, and we're holding on to nodes, let's bring those nodes back. So we have something like that right there. And let's continue iterating. Now we went from 12, now we're at 9, and then now we're on 10. And 10 is pointing to nothing. But like I said, since we have nodes on hold, the 4, 5, and 6, let's bring it and change it. And put it in front of the 10. So if we have this right here, we can bring the 4, 5, and 6 and put it right in front of the 10. And then we can continue iterating. We go from 10, then we go to 4, then we go to 5, and then we go to 6. And then since 6 is pointing at none, we check if we're holding any more nodes. But since we're not holding on to any more nodes, we know that we don't have to add anything and we can successfully finish. And if we were to look at the list now, we have 1, 2, 3, 7, 8, 11, 12, 9, 10, 4, 5, 6. And then here is 1, 2, 3, 7, 8, 11, 12, 9, 10, 4, 5, 6, and the exact same order. So that's really the main idea of this problem. Let's hold on to cur.next, right? And we can hold it in a data structure called a stack. And then remove the child pointer, make it point to none, and change the next pointer to look at that child list. And we only do this for nodes that do have child lists. So now that we talked about it, let's actually program it and see if it will work. So let's just create a temporary variable, or the root I like to call it the root. Set that equal to head. And let's create our stack initially empty. Now let's iterate over head. And if the current node, which is head, if that has a child, and if it has next nodes, so if it has a child and the next pointer is looking at some nodes, the reason we want this if is because the last node right here, the 6, could have a child, but it could not have any next nodes. So if it both has a child and next nodes, then we want to append to our stack those next nodes. Now we want to overwrite the next nodes and set it equal to the child lists. Then make head.next.previous equal to head. Because remember, we also have to update the previous pointers. This is something I forgot to mention in my drawing. I was doing a singly linked list, but we must remember this is doubly linked list. But it's really not that big of a difference. All that we want to do is when we make the child list in front of cur, then make sure that the first node in the child list is pointing back at the current. So change to 7. You see how its previous is none, right? Make that previous point to 3, because we're going to put the 7, 8, 9, and 10 in front of the 3. And then of course, like how we did mention, let's change the child pointer and set that equal to none. Check if not head.next. So we're at the end of our list. So if we're at the end of the list and we're holding nodes, aka our stack is not empty, then what we want to do is new underscore node is equal to stack.pop, and then add those new nodes. So head.next is equal to new node, and head.next.previous. Let's also update that previous pointer and make it equal to head. Then we are just going to normally iterate through the linked list by setting head equal to head.next. And then outside of that, we're done with all this logic, and now we can just return root. So that works, and now let's submit. And it works, perfect. So hopefully you guys are able to understand this problem now. It's a bit of a big problem to kind of tackle on because there's a lot going on. There's a lot of pointers that needs to be updated. But realistically, the main idea of it is that we want to store the next nodes for nodes that do have a child list. Then once we no longer have a head.next or a next node, and our stack is not empty, then let's pop our stack and add those nodes back in. Now this is going to be time complexity and space complexity are both going to be big O of n. Our stack might be the same size as the amount of nodes if every single node has a child, for example. And we're just going to be iterating through all the nodes just once, and that's where the big O of n for time complexity comes from. So other than that, hopefully you guys enjoyed the video. If you did, please leave a like and consider subscribing. And thank you for watching.